Hi, I'm Bill Summer. I'm the Director of Operations for Sane Engineering, and yes, I am the one who threw Kallie to the wolves. We call it professional development to give her an opportunity to stand up in an environment like this and present. The one thing I do need to point out in my own defense here is part of the provision of her speaking was she was going to be backed up by Jason Brooks, who is our technical director. He's the guy with the professional engineering license who has done a lot of the work that we're going to talk about. I did not. So any PEs in the room? Leave me alone. Jason.brooks@saneeng.com. He would love to talk to you about this.
Yeah.
I will do my best. I am knowledgeable, but I am definitely in that category of just knowledgeable enough to be dangerous in all this. So.
Okay, so let's get started. Our key goals here are to give you some definitions for what retrocommissioning and building tune-ups truly is, describe what kind of processes each one of those really entails, give you some examples of both, and hopefully as you're looking through the slides and hearing our examples of what we found, what we've done in your own buildings, you can say, oh, I've got that kind of equipment, I can do that. So those are the four main goals here as we go through this. So to start out, what are retrocommissioning, what are building tune-ups? So retrocommissioning is more of a systematic process. There's guidelines per ASHRAE of what really you need to do retrocommissioning in a building. You go through, you investigate, hopefully find some ECMs, energy conservation measures to hopefully then implement in your buildings. The building tune-up side of that is more of a free-for-all, a little bit less of a process that you have to follow. We like to go into the building, we like to talk to the occupants, talk to the facilities guys, talk to the owner, figure out what exactly are your problems, where can we come in and help, and hopefully we're building that relationship as that project goes on. So maybe we start out doing a little bit in the plant and then kind of show our value a little bit, and then hopefully, okay, what else do you have? Okay, what else do you have? So it's an ongoing process of hopefully just building that and coming up with more and more savings measures.
So as Kallie mentioned, we just kind of put this in a side-by-side. So retrocommissioning, as she said, very formally or much more formally defined for a lot of our government clients, federal government, when we go in to do this process, they want the full process because they want the nice 3-ring binder at the end of it that they can put on the shelf and forget about forever. We have a good number of commercial clients who are like, I don't really care about the paperwork, I just need you to fix it. Can you do that for me? And that's kind of where for lack of a better word, the marketing name on the building tune-ups came from, was you know what, we can forego the glossy report and all that and get to the point where we take those hours and get into the let's make it right. And so it is on site, it's using that time, that effort to interview the occupants, work with the facilities personnel, because again, they're the ones who know what equipment is behaving which way. They just likely haven't had time to go take care of it. And so when we arrive, we're not trying to come in as the pros from over to tell you you're running your business wrong. We're there as that extra set of hands to help you improve on things. In fact, Kallie will talk about one of our more favored clients a little later in that kind of relationship. So if I were to say it any other way, is in a building tune-up, it is much more of a relationship between us. We are a partner working alongside over the long-term, slow burn solution, as opposed to sweep in on a retrocommissioning, knock it out, document it, and move on. So some of the building types we're going to talk about here. These are just for our examples. The building tune-up can work for virtually any building type. But we're going to talk here about some office buildings, particularly some medical office buildings, community college, healthcare buildings in the course of this.
So as Bill mentioned, one of our favorite clients is this one up in Huntsville. It's a telecommunications manufacturer. They have essentially what they consider 3 towers, the north and south, and then the east. The north and south are kind of combined as one tower with a manufacturing floor on the bottom level. Primarily office space. They do have those manufacturing floors in the bottom of each of the north and south towers and the east tower. A few lab spaces too here and there, and so a lot of different types of requirements for each different space. It's about 1.4 million square foot, all electric, so a lot of room for energy savings. And so they've been doing that since about 2005. The energy manager here, he considers us part of his team just because way back when someone did phase 1 for him, and then he was pleased, so now we're on phase like 8 of basically building tune-ups for him. So he also gives us a little bit of free reign on his BAS. He's got the train tracer, so at the end of this presentation I'll show you some dashboards that we were able to do. But it's a lot of fun working with him just because he knows the value of energy savings, and he knows the value of where we can come in and help with that. Aside from those office type buildings, some of our examples here will be for the 2-year college system. This is just one of the community colleges that we worked with. There's a math and science building that I know that we worked in, and I think we've got 2 or 3 other ones, but I don't want to give you any specifics because I may be leading you astray on that. But this is just another of the community colleges, and we are out of Alabama, so this is where these primarily are.
All right, so another one of our clients is the Alabama State Capitol. So the architect of our Capitol, in this case, it's an old Capitol building with all the things that come with a building. Some of the solutions we're going to talk about here, in the case of Alabama State Capitol, the call or the reason we were brought in there, humidity. Shocker, Alabama. Humidity issues in the Capitol building, to the point where literally like the laws after the governor signs were like sticking together, and it was destroying the legal record. So that was the 911 call that we received, and it was pretty flattering because they came directly to us. They were able to use their emergency contracting authorities and go straight to us because they knew of us because of our work with the community college system, and said, we're pretty sure you guys can come in and help, and indeed we were able to. Another client that would be an absolutely private type client. This doctor actually owns this building, so the practice owns the whole building and structure that day. He just knew his building wasn't quite right, and said, I need somebody to come take a look at this, and how can you help? And a 40,000 square foot building there. Now, everything we're going to talk about coming up here, some of the cases of like both problems and solutions. To be honest, and we inserted this slide last night because it was in truth, almost every single one of our solutions in some way, shape, or form is going to end up boiling down to the affinity laws. That's where the power savings was when we talk about what we were doing. It just comes down to the pump and fan affinity laws. And probably the fan law 3 there, again, also works for the pumps. Probably this one here is just, this is where the savings are. If we can bring down pump speeds, fan speeds, we are saving power at the cube, the rate of the cube. It is a powerful tool. And so that is the lens to which we start to look at things, is how can we go about doing it? What we'll see in some of the examples we're going to give here, sometimes it isn't so intuitive, and we even had some counterintuitive results along the way. Now, one of the starting points we did want to talk about, because we see this one fairly often, is where are things like the pressure differential sensed at? Inevitably, a lot of times during construction, because it's the lowest cost method and the easiest thing, and the controls contractor wants to get in and get out at the lowest possible cost, they'll put the DP sensor there in the mechanical room, just supply, return, boom, let's go. Well, when controlling off of that, you're now, picture 1,000 words here. The control curve that the VSD can control across is fairly limited at that point, because you're going to be going with a relatively high set point on the system. And so what the VSD can or cannot adjust across is somewhat represented by this blue shaded area here. So if we can actually take the time and effort, and this does cost a little bit of money on this one, but not a lot, get the sensor out at what we'll call the far end here, and at the furthest branch, the furthest served equipment, get the delta P measurement there and set our set point off of that. It allows the VSD or the BAS to control across a much wider portion of that fan curve or pump curve. And that blue area represents the potentials for your energy savings. And so that there is a combination of move the sensor and then find what that new measuring point ought to be.
So another way to basically tune your building is to consider what outside airflow rates you are bringing into your building. A lot of times the spaces may change, and per the ASHRAE 62.1 standard, different space types require different types of outside airflow rates. So if you have this is one of our examples, but if you have a wood shop that then got turned into a storage room, you don't really need more outside air for that space. You could actually bring in less. And then, so that's one way. If your space types change, then refer back to ASHRAE 62.1 and see, okay, what outside air do I need in each of these spaces? And you could potentially bring in less for your air handler to have to condition. Another way to consider how much outside air you're truly bringing in besides of space type, during the design process, your occupancy for your outside airflow rate calculations, not all the times, but a lot of times, are based on default values that ASHRAE gives you. If you know your occupancies have changed or they're not as high as those default values, especially after COVID when a lot of people aren't in the space anymore, you could bring in less outside air to have to ventilate for those people. So terminal unit logic. One thing that we found at actually AdTran, our favorite customer, one of our favorites, I guess, not top favorite, but they have SWUD units, which are self-contained, water-cooled, unitary device units. So basically just a water cooling air handler. But we came in, and I forget how many they have, but it's a number of them, and they were all running at 40% VFD speed. We simply just asked the question, why are they all set to 40%? Well, the building owner said, well, way back when, for 15 years ago, when they put this in, the units would trip at anything less than 40%, so we just set them all to a minimum of 40 and left them alone, and they've been running. So then we were like, I don't think that's right, so let's investigate a little bit. Turns out the CTs were actually installed on the line side of the drive where the amperage is lower, and so at those lower speeds it was starting to trip, but those CTs were supposed to be installed on the load side of the drive, so all we did was relocate those CTs. All of a sudden they're running at lower speeds, back to the fan laws, saving money. Another way, so make sure your CTs are located correctly. Another way to potentially save some money on your TU logic, if you have PIUs or power induction units, basically VAVs, but they have a fan attached to them, in unoccupied mode, if that space needs heating, you don't necessarily have to bring on an air handler to go condition that space. You can just use that plenum air going through those PIUs, using that fan, using that heating cool or electric heat to reheat the space and not even have to ever bring on the air handler, which that is only if they're heating mode. But that's just another thing that in design, a lot of people don't program it that way just because they see a PIU as a VAV, but they are different units or different types of units. So lastly, CO2. Implement demand control ventilation. You can install some CO2 meters and then ramp down those flow rates. If the space is unoccupied, then you don't need to ventilate the space. So all of this just goes back to trying to reduce that air handler energy, because that's where your savings is going to be.
All right, and this next example, again at AdTran, had to do with the chiller staging, and so very the existing operation, that's an eye chart for everybody here, but it was just the standard sort of, hey, bring the second chiller on once supply temperature gets 2.5 degrees above set point, bring on the next chiller. By watching and observing the building over time, and that's literally being in the building and watching it do its daily cycle through the summer and things of this nature, it became apparent that the second chiller, and this is Alabama, North Alabama, summertime, that second chiller was slamming on at right around 3 o'clock in the afternoon, and then right about 3:30, everybody's walking out the front door, and that chiller would carry on for a little bit till, it hit its threshold to destage, and then it would stage off. And Jason, in particular, said, well, wait a minute here. Did we ever really need that second chiller to come on? Because by the time it might be sensed as uncomfortable in the building, everybody was walking out the door anyway at end of day. Could we put in some logic to delay the instance or the need for that second chiller to come on? So a three-stage, when I say three-stage, a three-step logic was just written into the code there. It says, yeah, you know what, in the morning, we actually need to get the building up to temperature real quick, so we're going to go with the 3.5 degree before bringing the chiller up. Now, if you have to add another chiller, we're actually going to bring this to a 4.5 degree, just to stretch out the time limit, because more often than not, by the time that extra chiller was needed, people were actually heading out the door. And we could just kind of coast the building, let everybody leave, the labs are shutting down, and then let the evening time with the existing chiller recover everything for the next day. Now, certainly, when you get those, 105 degree days with all the humidity in Alabama, the second chiller's coming on and you're running with it. But that really helped delay a lot of the start just by being a little more, or taking a little extra time before deciding to bring that extra chiller up. Tower and the tower pump. So Kallie mentioned that these SWUD units are a little interesting in that you're actually moving condenser water into the building to get to the SWUD unit, which is then going to do the heat exchange to send onto the cooling coils. The as-is condition, the pumps would ramp to maximum, and then the cooling tower would start to bring its fan up. Jason and team put the fluke meters, tracking fluke meters on the pumps and on the tower, watch the behavior, plot it out, see their behaviors over time, came up with performance curves, looked at it and said, well, wait a minute. Interestingly enough, in terms of the effective cooling that could be achieved, they found out that if we match the pump and the cooling towers and ramp them together, they got the same effective cooling as opposed to running the pump up to say, it's full 20 kW, and then starting to ramp up the tower. If they were just both, tower and pump at, say, 5 kW each, they were getting the same effective cooling effect on the system. And so that was purely a watch the behavior of the system, plot it, track it, and then Jason putting his engineer mind to the problem, saying, hey, wait a minute, we think there is another way we can sequence these to trim the load. Very similarly, condenser water pumps out at the other tower, common configuration. There were 2 condenser water pumps in parallel. As his condition was, and this took me a while to read his graph, pumps are on, these lines are when the pump is momentarily turned off, but then, summertime, it is 2 pumps running constantly. Now, if you look in the ASHRAE publication, it will tell you if you've got 2 pumps in parallel on the system, that second pump really is, you're going from a 1.0 pumping to maybe a 1.4, theoretically. Put the ultrasonic flow meter on the system, stage the pumps, watch, observe, discover that at best, that second pump was adding bringing the system to about a 1.25. And in reality, for the conditions of the area, it became more and more evident that there is never a reason for that second pump to have run, ever. It really could just go to lead lag. So We go into the system, we change the code, we change the programming ourselves, and get them that efficiency of that second pump being removed from the system.
So for this setup, the supply temperature that was supposed to be going to the building was actually 40 degrees. We know that's very low typically. For this building, it was serving lab spaces, so we had to have it that cold. With that being said, the water that was supposed to be going into the heat exchanger, or coming out of the heat exchanger, had to be 36 degrees. So we noticed an issue with it being able to maintain those pretty strict set points, and we looked into it a little bit. Turns out the cold water basin heater in the cooling tower's set point was higher than the 36 degrees, so it was just a never-ending cycle of trying to cool off that heat that was gained through going the cooling tower. So once we figured that out, changed set points, all of a sudden it's running way more efficiently. So.
By the way, it's worth sort of a side mention on this one, because that turned into one of those symptoms that we now we see cooling towers. Like, one of the first question now is, what the heck is the basin hot or the basin cold water thermostat set at compared to what the desired economizer rule is. But one of the other places we saw an interesting challenge, and we put it out there as kind of the asterisk to the story. Folks who are looking to do waterside economizing, if your cooling towers are concrete basin or concrete basin in ground, recognize that you have a heck of a heat sink to overcome before your system's going to want to drop into economizer mode, if it's going to do so at all, because of just the mass of that concrete. That depending upon, again, your region where you're at, in a place like Alabama, yes, it does get cold in the wintertime. It can hit 10 degrees, things like that. But it does so very rapidly for a few days, and then you spring out. So something that has something like a concrete cooling basin or something of that nature is never the temperature for that economizer to really be able to come in on the water side, because the water will still hit the cold water basin, get warmed up by the earth, warmed up by the concrete, and then operating the way you want it to. So that's the asterisk kind of on that story there.
One more thing with cooling towers, if you have multiple cells and your turn down ratio is pretty decent, try to not ramp up the fan in one cell and then bring on the other cells. It's more efficient if you run all fans at the same lower speed rather than that one fan at a higher speed. You just save energy back to the fan walls.
Yep, back to the fan walls.
So one of the community colleges that we actually worked with was trying to do the right thing. This was, I think, 15 to 20 years ago. They decided they wanted to do a PV array, and it was sized pretty good. It definitely handled the load during the week. And so on the weekends, it was actually gaining more than what they were using. However, communication is key. Try to work with your utility company and be involved throughout the whole thing, and make sure that instead of a unidirectional meter, you have a bidirectional meter installed, because otherwise you're going to be getting charged for sending them energy back, which is exactly what was happening here. They were noticing, why are my energy bills a little bit more than what they need to be? So we looked into it, told the utility company about it. The utility company took ownership, definitely, and as soon as they were notified, they were out there changing out the meter. But just try to keep that in mind as you do PV array, and try to do the right thing for the environment. Also make sure you're not getting charged double time for it.
Perhaps the cruel irony was the building that this was on was literally the community college's energy technology center used to teach students about setting up photovoltaic arrays, etc. And it's also worth noting, this is one of those problems that, again, like when we interview facilities folks, there was always, the electrician was like, there was just something in my gut for the last 12 years that something wasn't right.
So we do some work with TVA, which is Tennessee Valley Authority up near the Huntsville, Alabama, Tennessee area. They wanted some load shed. Well, we helped this community college with some TVA load shed. However, figured out for them, TVA or load shedding is easy, but sustaining that load shed can be difficult. So, as you do load sheds, you can either do resets, static pressure resets, discharge air temperature resets, instead of just trying to shut equipment off, because then that equipment has to come back on at some point. And so, changing set points can help you reduce that demand rather than just or reduce the load instead of just shutting equipment off. Another way is if your VAVs may serve hallways or storage rooms or anything, changing those minimum set points to 0 so that that's less airflow that the air handler fan has to provide can help save some energy. Another method is if you have a multi-floor building, try rolling the floors. If you do want to shut off equipment, maybe rolling the floors on who's actually in that load shed. So at some point, equipment is off, but it's not one floor that has to suffer the whole time. So that's just a few options there.
Unless you really don't like the guys on that floor. But I will pop back real quick. So yeah, the plot here, what we wanted to show, really kind of highlight there was, yeah, you can drop into the load shed, but eventually, you're not going to be able to sustain it continuously without incurring, when I say a cost of performance, a cost of comfort, or something like that. The equipment eventually is going to say, look, I got to come on if we're going to meet minimum thresholds. So having a good plan, and Kallie will later talk about a decently complex plan on how to prevent like this. Hey, we made load shed, but now our system is trying to self out of load to satisfy building loads. All right, next little vignette I want to talk about here, again, at a university or a college, Performing Arts Center. It's a big eye chart here, it's just for background. But the key part of the story here is the school was facing the fact that this Performing Arts Center, when the HVAC was cycling on, it was roaring, which is a little unpleasant for the Fine Arts Center to have performances with the HVAC screaming at them. They were to the point where they were about to start tearing out walls and reducting because it was that much of a disruption. A little bit of an examination. I'm pulling the paperwork on when this was built. What the heck? Because it seems very odd that that the builder was ever even walking away from it with it behaving this way. And as it turns out, it became apparent that the duct sizing was absolutely correct for standard duct. But the minute you put the acoustic liner in it, you've changed the duct airflow characteristics. And to overcome that airflow, the air handler is ramping itself to max speed. So the solution to this one, I actually have to step up on the stage here for a second because this one was a little bit counter. I'll just put it over your shoulder. So the solution on this one here was going in, changing the programming between the chill water valve and the fan such that we actually run the fan minimum, modulate the chill water until the chill water eventually would be at max, then slowly start to bring the fan speed up. And the net effect on that was, well, we got really good moisture extraction, but the other part of that was the fan rarely needed to cycle to its full extent at that point. So we really took what was otherwise being operated as a constant volume system, and we're able to bring it into a variable speed operation by first starting with chill water flow, and then bringing the fan speed up on that one. Well, the trade space on this was, otherwise we're reducting, or the school's reducting. And so yes, that was the trade space there, the workable solution to get an acoustically acceptable performing arts center in that case was, let's take this thing, discontinue the programming where, again, it was treating it as a constant volume system. So we were actually getting some goodness out of this on the energy savings, because by adjusting the chill water flow first, it goes to max chill water through the coils before ramping the fan speed up at this point. It was not intuitive, but the net result got the school something that was acoustically acceptable. So the air handler now basically operating as variable speed at the cost of, yes, we're flowing more chill water, but no more chill water than what the coil is capable of doing. So, but that's, I think what I like about this particular vignette is it highlights one of the things we see here. This one, or the one with the vignette about the 2 condenser water pumps, was there's the design, and a building that's commissioned, and we do new construction commissioning, a building that's commissioned on new construction, I'm going in to ensure that it is meeting the owner's requirements, but that those owner's requirements, as interpreted by the engineer of record, does the sequence of operation, everything go in accordance with the engineer, because he owns it. After that warranty expires on that building, we can go in and we can start making adjustments. And when you measure and observe and discover that, and I'm not knocking architects and engineers, it's just the reality. There's what is designed, and then there's the way it actually performs. And sometimes you have to adapt to that actual. And so part of the building optimization process here is, how do we effectively adapt to that actual case in a way that keeps costs in control for the owner? That was a lot of words, sorry.
As I mentioned kind of before with the outside air, as your spaces change, aside from how much outside air you need to bring into the space changing, also your temperature and humidity requirements may change too. As I mentioned before, this was the site I was talking about. That was a wood shop, pretty large area that for the woodworking items, equipment, and finished products, certain temperatures and humidities were required to maintain the quality of that equipment and for those products that the students were making. However, when they transitioned this large space into a storage room, no one changed the programming, so it was still keeping those tight temperature and humidity requirements for really no need. So as you change spaces, try to make sure that if you are able to spread out those set points and able to reduce the mechanical heating or cooling, or even the fan speeds, any way that you can do that to just take the load off the air handler a little bit will end up helping save you on your energy bills. Honeycombs. So, they've got a good intent. However, if they're not clean, they end up being an obstruction in the ductwork. So if you have an existing building and there's honeycombs there, try to add access panels. And if you have a new building that they're installing them, try to advocate, put access panels there for it, because we've been in buildings where they're like, yeah, there's a honeycomb, but we had to cut the ductwork and then wet it back together to clean the thing. Another note on this slide, if you have occupant complaints about too much airflow in a space, try not to crimp the ductwork to reduce those airflows. They do make dampers that can do that for you. So that was just
in all fairness, a facilities guy is not the one who crimped
True.
the ductwork in lieu of a damper. That was a faculty member who did that one.
Yeah.
But
Yeah. A lot of buildings have leaking valves. Leaking valves are probably one of the easiest things to diagnose in a building, especially if you've got a VAS. Just run through there and command all those valves shut. If the temperature between the mixed air and the supply air is anything more than maybe 2 to 3 degrees, if the sensors are calibrated, then you probably have a leak somewhere, because the only heat it should be picking up is maybe a little bit off the fan. So as you go through, that's just, and it may not be as drastic as 95 to 55 having to cool off, but I wish I had the numbers on hand, but any degree more that you have to mechanically cool or heat is money that you're spending. Question? We typically try to advocate for percent open.
Oh, yes.
For the controls techs that we work with, if they try to argue one way or the other, we usually say, look, we don't really care what you end up doing. If the owner does not care, then we do not care as commissioning agents. However, on your BAS, please put percent value open or percent value closed so that there are no questions in the future, because I'm not trying to have two dampers closed off to a running fan.
And if it's a new installation, be consistent with the previous installation.
So for this unit, it's a DX cooling unit, and we came in and trying to be snazzy and add programming to reduce some energy on the fan running. Everything goes back to fan laws. So we try to do a static pressure reset instead of running that fan at a constant static pressure. However, it was going to void the warranty if we did that while the compressors were running, because the compressors required a certain amount of airflow going across them. So we kind of found a loophole and talked to the manufacturer and asked, okay, if it's in air side economizer mode, then can we reset the fan to slow down? The compressors are locked out. That's not going to be an issue anymore. And then after talking to them, they were like, well, I guess so. It doesn't say anywhere that you can't do that. So even when you think there may not be an option to save some money, there may be a way. It may be small, but honestly, anything small is money saved, in my opinion. So,
Yes. And to be clear, the manufacturer signed off on it. They just had not envisioned that particular use case. That you're right. The compressors are locked out. I guess there's no reason you can't ramp the fan down to a minimum. They just had not considered that use case in the design of their package unit.
So, like Bill said, humidity issues are a very common thing in Alabama. And so we usually include this slide in presentations because even if you don't have a dehumidification sequence programmed in your units, but maybe you're having humidity issues, if you have this kind of setup where you have cooling cool and then reheat, you're able to dehumidify. Even if you don't have a temperature sensor directly after that cooling cool, that would be best case scenario so that you can actually control that valve to 53 degrees, 55 degrees, and then reheat the air back up to maintain that space temp. But yeah, this is strictly, if you have this set up and you have humidity issues, then you have an opportunity to be able to dehumidify your space. As long as you have a humidity sensor in the space or a return ductwork. So.
Okay, on this next one here, fairly simple. We talked about this early on when I was showing the piping diagram again. Same thing on the air side. That pressure sensor, if they've parked it here inside the mechanical room, the envelope of control on that VSD is not going to be as wide as if we can get that at the distant end and control to that static pressure set point. We can again generally allow the VSD or VFD to follow its programming over a wider range of operating points and get that fan speed down for longer periods of time. There we go.
So for this setup, we had a condenser water loop, and it was just running at a constant DP set point. So we were able to implement a reset for that DP to actually maintain a differential temperature of 10 degrees between the supply and the return through that loop. A lot of water systems endure through low delta T syndrome, where it's not really ever doing much cooling. And so if you want to maintain a certain delta T, then there's a direct relationship with the flow through the system for the capacity of that loop. And so if you reduce flow, then you can increase delta T and vice versa. So we implemented a program where we said, okay, we want it to be a 10 degree delta. If it's greater than 10 degrees, let's speed that pump up. If it's less than 10 degrees, let's slow it down to try to maintain that. So that's for a condenser water loop that we did that for, but if you have a pump in any system that is running at a constant DP, then you're able to do this. It's pretty snazzy, I think. So.
All right, so one of the other things that we use as a diagnostic tool is we go about measuring throughout the system the static pressures. And what we're looking for is the unexpected pressure changes given that particular point in the system. So it's just a very generic graphic here, but one of the cases that we can run into, and in fact we did at a sporting facility, what we're expecting to see is good positive pressure there at the relief. Or this is the system we want. There we go. Can get this right. Yes, we want to be seeing positive pressure there in the relief, a little bit of negative pressure there in the mixing box. Without that, what we really ran into was we had a system where we measured and there were negative pressure at the relief damper. And the result of negative pressure at the relief damper is the system was then trying to pull any outside air this direction, and we were actually not getting the outside air we needed into the building. That was diagnosed by just running around pulling pressures on the system and go, wait a minute, that doesn't make sense. So just a little vignette, again, using pressure measurements, static pressure measurements on the air side as a diagnostic tool to go, are we expecting the right pressures at the right places along the right spot of the pathway there?
Another indication with this system, though, if you want to make sure that you're actually bringing in outside air, if you think you've got any issues with that, along with if you have a return fan system, making sure that that is not a negative number up there, but also if you have a mixed air plenum, if it's a positive pressure, then you're probably not bringing in outside air. I guess in this system.
Yep.
Before I speak wrong. Okay.
Okay, here we go. Sorry, got to do my cheat sheet again here. Oh yes, there we go. So one of the other challenges, again, Alabama, lots of humidity, but we do have a winter, and so we do strive to be able to do airside economizing. A lot of times, particular package units and others will use an enthalpy-based, that is wet bulb-based logic for the decision for the system to go into economizer mode. And it is in a perfect world, that is the optimal way to do it, would be to follow the wet bulb. What's the liability? The liability is humidity sensors tend to fail more often than, say, dry bulb sensors. And when they fail, they tend to fail low. And what we were observing in time at these buildings was if the logic was set that for enthalpy as the driver to go into airside economizing mode, once the humidistat starts to fail, it was dropping the unit into economizer when it was not appropriate to do so. And so then they were pulling in all that extra very warm, very moist Alabama air. And by switching the systems to doing dry bulb economizer, because dry bulb measurements were more reliable, we were alleviating the tendency for those units when they fail to fall into economizer mode prematurely. And the net result is energy savings because we were avoiding having these systems fail the wrong direction. It's just a little bit of the hazards with the humidistats, but we found overall the less risky and still energy saving method was to go with the dry bulb logic on the airside economizer. All right.
Okay, so this is my baby, so to speak. So we did demand load shed for Adtran that we mentioned a few times. Like I mentioned before, they have essentially two towers, that north and south tower and the east tower, all electric. I'm not going to read the slide. You can see what equipment they had in each of those buildings. So the first step was figuring out what exactly that load shed was going to look like. So we talked to that facility manager / energy manager at the building to see, okay, what what kind of setup do you really want? And the end goal, I think, was let's do something that is relatively hands off. I don't want to have to go in and change the set point every month, every week, every year. And so I've got a coworker that helped me on this project too, and he was some of the brains behind the model for it. And it's a big math slide that I did not include on purpose on this one. But basically, every month it looks at the previous month and alters that set point to reflect what it's probably going to expect. And it does that on a yearly basis. And so it's constantly changing, constantly learning, okay, this is about what the load was for this month. And so that was the set point brains behind it, instead of changing the set point manually. Or having a constant set point throughout the year, because it is Alabama. We have those cold months, we have those hot months, so it does not really make sense to do one set point all year long. Another thing that we had to kind of consider is, do we want it's all or nothing load shed, or do we want to stage it? And we did end up going with the staged method because we didn't want to cause the facility manager and all his guys to have a bunch of complaints when the occupants in the offices don't know what load shed is and don't know that it's actually being implemented, and then he's getting 20 calls because the air feels a little bit warmer or the fan slowed down, and so it feels like less airflow. And so we tried to stage it so much so that it was very gradual and it wasn't as noticeable. And along with that, if we can do less but accomplish the goal, then we win. Because if we don't have to do all of what's involved with stage 5 and we can just do stage 1 and still keep that load down, then that was great. So the scheme of the load shed, I know this is kind of a busy slide, but this is how we separated what exactly we did. You can see what tower, what kind of equipment it went with, what the parameter was, and what exactly was going on with each of those parameters. And you can see with each stage and what those set points were, we didn't want to do it too drastic where it was going to cause a bunch of complaints, but we wanted to do it just enough where it was reducing that mechanical cooling load, reducing that mechanical heating load, reducing those fan speeds, cutting off the non-critical equipment. So a little bit more about the measures. For the SCUs or the air handlers, we did discharge air temperature low limit resets so that it was basically kind of spreading out that band a little bit of what it was having to maintain. We did discharge air pressure high limit changes so that it was allowing for the fan to slow down and not have to ramp up as much as what it would in normal operation. And then, simple as it can be, just shut it off if you don't need it. So onto the VAVs, their BAS allowed for the thumb wheel control to be locked out or enabled, and so we locked it out so that the occupants couldn't bump it down to 67 degrees, and we kind of had it at maybe 69 to 74 for stage 1, and I don't remember the exact numbers that were on that previous slide, but instead of allowing for them to ramp it up or ramp it down, we kind of had it a little bit more set during those load shed times. And we spread out the cooling and heating set points and used the aux sensors that were installed in the building to show if it was unoccupied. Let's put it in standby mode and close it down. So, we had an easy button. So, and I've got some dashboards because this was part of the train tracer. The facility manager actually wanted us to show him, can he see it in real time what's going on? So I'll get to that and I'll show you. So they had some fan coil units in some storage rooms, and I think they had a number of them in a manufacturing warehouse. And so we rolled those and had half of them shut off, and so that was able to reduce the load. And then the lighting, that was really for stage 5, but we had hallways where if we really needed to cut that load, then we were shutting off the corridors or the hallways, shutting the lights off. And at first, people did wonder, why are the lights going off in the middle of the day if it really needed to do stage 5? And after they learned what was going on, no one really cared because they were in their office and they can deal with a little bit of less light going through the hallway to the restroom. So as we were programming it, we were running through its test, and you can see one graph is the north and south tower, the other graph is the east tower. While we were testing it, you can see where that load dropped off, and we actually were able to see our work in action, which was pretty cool. So onto the pretty dashboards that we got to create, which were fun. So this is pretty much the main load shed screen. You can manually put in a certain floor in load shed, as well as completely disable a floor if you know that you have, like they had some major conference areas, and they knew if they had an event and they put it in load shed, they were about to have some angry people, so they were like, no, shut off that floor, let the other floors go into the load shed. So that gave the facility manager complete control over the load shed programming that we did. But if he left it alone, then all of those floors were looking at that master load shed stage, and all of it was controlling together. And we had it, you can see where it says no load shed. That's if it was at stage 0. If he overrode that point, the master load shed, then that master load shed calls would show manual override, or it would show, I think just demand load shed of, it was looking at that set point and it needed to go into it automatically, so it did. So those were the key components of that dashboard. He also wanted if I get hit by the bus, someone's got to take this over concept. And so we included this where if any new guys came on and they said, what do you have in this building? If he brought up load shed, this was his easy dashboard to say, this is what I've got, this is what it does. As well as any C-suite people that were asking about it too. This is the very clear, I guess, somewhat clear.
It's clear to me.
Yeah, clear to me, but they're saying something. But dashboard that he can show and say, this is what goes on in my building during load shed. And he is their energy manager, so he is heavy on energy savings in his building. So this was part of the project too, where he wanted to show all of his energy savings, and so this was a pretty fun dashboard to, I guess I can't thank this one wasn't fun, but it's fun to look at. So, any questions on this? Okay, and then, like I said, he is heavy on the energy savings, and the company puts out dashboards every so often that they create, their marketing team does, of pretty much the energy conversions that show how many light bulbs got turned off or how many homes. So he asked for that for this project, and so yeah, since 2005 they've been able to reduce their EUI pretty substantially, and I think now this is an older picture. They I think now have 9 million wind wrecks, if I'm remembering that correctly, but I could be wrong.
I do not know their wind wreck number.
Yeah, I'm not sure. But, so, this one was my dashboard. So, this one's mine. Some project results. So, when we went into that load shed project, we calculated that we were about to save the company about $27,600 annually. After testing the actual results, we were able to see that we were saving close to $36,000, which was pretty rewarding, as is. These were, I don't know the answer to that question, actually.
That was his first year?
I think that was his first year where he was actually looking at the data. And one thing we have added since then is TVA came to him and said, will you participate in a demand load response where if I call you and ask you, reduce your demand load, will you do it? And so we implemented that in a project following this one where Train came in and installed a manual switch and then added a point to their BAS where he can go onto their BAS and say, I need to do this demand load now. And since our existing programming was already there, it goes straight to that stage 5, all hands on deck, and good to go. So, but I do believe that was in their first year of it actually working as is, not in our simulation testing. Last slide, thank you for bearing with me. These were some of the results of basically somebody that we came in, we helped save energy, but then maybe a contract wasn't renewed. That's not the point. But if you have energy savings going on in your building and then step away from it, no one's watching it, it will walk away from you. It will start creeping back up. And so just try to keep that in mind.
Energy savings earned at that point, we're good for that point. But yes, if you turn your back, it will take over.
And I know it's 3:10, but are there any last questions?
Well, the hard part on that, and the reason I'm not comfortable, is because that is over several years of that. Again, that was a relationship that was piece by piece by piece by piece. So
But just the demand load, I'm not sure.
So the demand load shed. How much did?
Was that a 2-year payback?
See, I'm having. I honestly would have a hard time
I'm not sure the
recalling.
number on that.
What I will say, here we go. We'll back up here because I think it shows up on this other slide. Okay, no. So the client gave us an email at the beginning of the year with the, hey, it's winter break. We all went home. I did the math, and hey, did you know? Together we, and it very much is a we. Again, Kallie himself is a world-class energy manager, but he views us as a team, and he goes, hey, you know, since like 2012, we've saved about $14 million. I was like, wow, we should have gone shared savings with you. Really was our answer to that, because no, we did not charge him anything near that. He got a fabulous return on investment over the last 12 years on the level of work. So long-winded non-answer, but yeah, it's most everything we've talked about here. This was time. This was labor to go watch, maybe rig up a sensor for a little bit at a time. So very, very low paying. I see another hand pop up over. No other questions?
I think most presentations say fill out a survey, so I
That's
guess
right.
fill out a survey.
Just remember, this was her first time on the big stage.